discussion section has been set to Tuesday at 4, and yeah, office hours are still TBA.
What are you waiting for? More polls?
Yeah, I just want to I just want to maybe give a little bit more of a chance for people to respond, but I'll send out an announcement soon.
Okay, I understand you do have conflict with the seminars, though. Are you sure that's okay?
Yeah, they told us, right, that we couldn't move it unless there was a time that fit for everybody, right? And of course, and there unfortunately wasn't a common time.
Okay. All right. So
yeah.
for you who have not filled out Doodle poll, please do so to help Reggie. Okay.
Yeah. Thanks.
All right. So let us get started with the lecture, and it is recorded, being recorded. So that's good. And let me get started here. All right. So this is the third lecture on quantum field theory. Just to be sure, can you see the cursor? Yes. Okay. Good. All right. So let me get started. So well, we were talking about the coherent state of the harmonic oscillator. So let me finish up this discussion. Then finally, we actually do move into quantum field theory today. So that's the plan. All right. So what we have been talking about about harmonic oscillator is to take this annihilation operator, and we discovered that the number of states are actually not minimal uncertainty states. If you go to large n, then actually uncertainty grows, despite the expectation that large n should correspond to, in some way, classical limit. So that was a little surprising, and a poll certainly was divided on this, and that reflects that this was a surprise, at least for some people. And we try to come up with some intuitive understanding on what's going on, why large n would lead to larger uncertainty. And this is where I start to draw pictures like this. So classical motion has x and p well-defined at any moment at the same time. So that corresponds to a little dot on this plane. And a harmonic oscillator goes from large x and goes down to small x, they go to negative x, then come back. And also at the same time, velocity would pick up as the pendulum swings towards the middle. So it would actually give you this kind of circle as time develops. And the classical particle is a dot on this circle and keeps moving like this. On the other hand, number state has basically energy to be well defined, that's x plus p squared. And so what that would correspond to a band like this. So the number eigenstate has both x and p uncertain, that's why it's a band instead of a single circle. And the x plus p squared is basically defined, n. So here I'm drawing a circle from n plus 1 to represent the fact that number is not a continuous number in quantum mechanics, but rather discrete integers. So it takes only in one step at a time. So that basically gives you kind of thickness in n if you try to depict it this way. And so that actually ended up being rather large area and therefore large uncertainty. So x and p are large, so that also makes the uncertainty large. So what we like to see then is that, well, the part of the reason why the uncertainty is very large here is that the expectation value of x and p both vanish in the case of number eigenstates. And the delta x and delta p is defined by expectation value of x squared minus x expectation value squared. And that's the way dispersion or uncertainty is always defined. So given that the expectation value itself vanishes, even if you have a x squared expectation value and subtract the expectation value squared, expectation value squared is just 0. So it gets dominated by x squared expectation value and also p squared expectation value. And that's something order n because of that. So that's how you end up with uncertainty that actually grows with n. So the fact that x and p expectation value vanishes is making this uncertainty rather large. So if you want to have a state, quantum state, that mimics the classical motion of the pendulum the most, then you'd rather have a state where x and p expectation values are non-vanishing, so that it roughly corresponds to some particular possession of the pendulum. in particular motion of the pendulum. So we want both x and p to be non-vanishing. So what we want is a state like this, where you have expectation value of x and p somewhat more or less well-defined. And of course, it's quantum mechanics, so area can never be smaller than h bar over 2, but it can be as small as the uncertainty of the ground state, that's this red one over here, where delta x delta p is really h bar over 2. So that would be what we call the minimum uncertainty state. And so we are looking for a state like this one, namely that we have this minimum area, which is h bar over 2. X has some expectation value. P also has some expectation value. So we're looking for a state where you can define x and p simultaneously, more or less. And we all know x and p cannot be specified exactly at the same time because x and p don't commute. Therefore, there's no simultaneous eigenstate of x and p operators. So that you cannot do, never do. That will make Heisenberg very unhappy. But we are looking for a state where x and p are more or less well-defined. And so we are looking for that kind of state. So that is what we are calling coherent state, where x is more or less at some value x naught, p is more or less at some value p naught, and it occupies some area to make Mr. Heisenberg happy. And that would be this little circle over here. So how can we come up with a state like that is the question we posed the last time. And so here's the answer. So we are looking for now an eigenstate of the annihilation operator. And that's when I said, huh? Because we always talked about eigenstates of Hermitian operators, and eigenvalues are all observables, namely real numbers. But annihilation operator obviously is not a Hermitian operator because A and A dagger are different and they don't commute. A dagger commutator is 1. So talking about eigenstate of an operator that is not Hermitian is probably something you have not seen before, but it turns out that this is actually very helpful in this context. And the reason being that annihilation operator is x minus IP. When you take the limit where h bar, m, and omega are all 1, A is just basically given by x minus IP over square root 2. So if A has an eigenvalue, then you basically specified x and p at the same time. What that means, though, is that eigenvalue is necessarily complex. It's not a real number. But that's good because if f is a complex number, the real part of f should correspond to x. Imaginary part of f should correspond to p. So knowing f as a whole complex number with both real and imaginary part, you basically specified both x and p. So that would be a great state to have if there is such a thing. So once you have a state which satisfies this requirement that acting annihilation operator on it, and you get this complex eigenvalue f, that would be a state where you know what x and p are at the same time within the uncertainty allowed by Mr. Heisenberg. So can we get a state like this? So if you have the state like this one, then you can immediately compute the expectation value of the x operator. An x operator in this unit is just a plus a dagger over square root 2. And a acting on the state f would pull out eigenvalue f. On the other hand, a dagger sandwiched between f state can be viewed as a dagger acting on f bra. So if you take a Hermitian conjugate of this, that's the same thing as a acting on f ket. That pulls out eigenvalue f, as we just talked about. But it's the Hermitian conjugate of a acting on f ket is what f bra with a dagger acting on it. So that eigenvalue will be f star. So expectation value of x is nothing but f plus f star over square root 2, which means that it's really the real part of this complex number f, as we just talked about. So having this eigenvalue f as a complex number really does mean that expectation value of x operator is this real part. And same thing with the momentum. So momentum operator can be written like this using creation and annihilation operator. Again, A pulls out eigenvalue F. A dagger would pull out eigenvalue F star from the bra. That's here. And so this is nothing but imaginary part of F, as we just argued just a minute ago. So having this eigenvalue F for the annihilation operator really does correspond to the finite, the expectation values of both X and P operators given by the real part and imaginary part of this complex number F. So as desired, we do have that kind of situation if you manage to find a state that satisfies this requirement. So the real question then is, how do we figure this out? How can we find such a state? And so in order to find this eigenvalue F, we focus on this commutation relation between A and A dagger. And this is a heuristic argument, and we have to actually come back and prove it. But if you look at this commutation relation, it looks as if A is a derivative with respect to A dagger. So remember, this is a heuristic. This is not a rigorous mathematical argument. So we have to come back and show this actually makes sense. But if you take this heuristic argument, then what you're looking for is to find the eigenvalue F when you take derivative with respect to A dagger. And we know such a function, which is just exponential. So if you take A dagger derivative acting on this exponential, then that will pull out F from the exponent, and that will be the eigenvalue. So that's the way we may hope to find its eigenstate of the annihilation operator by using this exponential of the creation operator. So I hope that makes sense. So what we then do is to try to see if we can really find such a state. And it turns out that this is the answer. So indeed, this is the exponential of the creation operator. And we define this exponential of an operator by the Taylor expansion. So exponential is Taylor expanded as 1 over n factorial times the exponent to the nth power. And when you have A dagger to the nth power acting on the ground state, that would raise the ground state n times. So you end up with the number state n, together with the normalization factor that's square root of n factorial. So when you expand, the Taylor expand this exponential, you had 1 over n factorial, but this state has norm square root n factorial. So that cancels the square root part of n factorial. Another square root now still remains in the denominator. At the same time, you have raised this whole exponent, not just A dagger, but together with F to the nth power. So this term would come with F to the nth. So at the end of the day, this exponential of the A dagger operator can be written as the sum of the series of F to the n over normalization factor the square root of n factorial on the number state n. And I had yet another factor of this e to the minus f star f over 2, which is there to keep this state normalized. So if you compute the norm of the state, then n sandwiches n becomes 1. You have f star n to the n and fn in the numerator. The denominator becomes squared, so you have n squared, n factorial down there. And so if you sum over f star n, f star to the n, f to the n over n factorial, you get exponential of f star f. And when you compute the norm, this factor also gets squared. So that's e to the minus f star f. So you get e to the f star f from this series. You get e to the minus f star f from this normalization factor. So they cancel and become 1. So that's how the state is actually normalized to unity. So this turns out to be a well-defined normalized state. And what you're supposed to do in the homework problem is to just act A on this. And with this form, you don't know really what to do, but with this expression, you do what to do, namely that an annihilation operator acts on this number state n. then it lowers the number from n to n minus 1, together with the normalization factor that's square root n. So n part of factorial gets canceled. N minus 1 factorial still remains in the square root in the denominator. But f is still raised to n power. So I have now n minus 1 state, n minus 1 factorial downstairs, but f to the n is still there with n power. So compared to the original state, I have one extra factor of n, so that gets pulled out to the front, and that becomes the eigenvalue of the annihilation operator. Now I see a hand up from Varun. Go ahead.
Yeah, Professor, should that be a sum on the first equality?
Ah, thank you. This is the typo. So I shouldn't have sum here.
Okay.
Yeah, there shouldn't be a sum here. So f state is defined to be just this operator, exponential of f a dagger, acting on the ground state, together with this normalization factor e to the minus f star f over 2, no sum because there's no n in here. So only after Taylor expanding this exponential, I start to get this sum over n, because each time you have a dagger to n power, you get the state n, and you need to sum over them. Thank you, Varun. So this is a typo. So I want to fix it before I post this on B courses later. Okay, but anyway, it's a good time to stop and pause and see if there are any further questions about this. Any more questions?
Sure, I guess I have one. So is the motivation for this, like this ansatz for A being the derivative of A dagger, just by comparing with the canonical commutation relation?
That's right. So looking at this A dagger commutation relation, so if I can treat A dagger as if it were a number, then to get this commutation relation, A should be derivative with respect to A dagger, right? So if there were some representation where A dagger is a number, then A has to be represented as a derivative with respect to A dagger, in much the same way that if you have XP commutator to be IH bar, then in X representation, P should be represented as X derivative, because they don't commute and become IH bar. So in the same way, if A dagger is treated as an eigenvalue of some sort, then A should be treated as a derivative with respect to A dagger. Of course, the question is whether this kind of expression makes sense at the operator level. It's not totally clear. That's why I said this is a heuristic argument. But that's what physicists are very good at. Physicists are not as rigorous as mathematicians are, but we are good at finding new rules by making this kind of heuristic arguments. So the physicists speak is, okay, A looks like A dagger derivative, so why not just take an exponential of A dagger to make sure that that pulls out the eigenvalue F? And it turns out that heuristic argument does work out in this case, which you're gonna show yourself in a homework problem, so that this definition without the sum, I have to repeat, which is given by this Taylor series, really does give you eigenvalue F when you act annihilation operator on this state. Okay, any questions about this? I hope you feel that you can do this yourself. It's okay? All right.
Oh, sorry, I also have a question. So the motivation for, looking for these coherent states as the eigenstates of the annihilation operator. So it's just that, that A contains information about both X and P. Like, is that?
That's right.
I guess I'm okay.
Yeah, and of course we have to justify this choice after the fact by demonstrating that coherent state, which we just defined, really does represent the minimum uncertain state, and also it mimics the classical motion of the pendulum as closely as possible. And you will see that demonstration in a couple of minutes.
Okay.
Thanks for the question. And any further questions? Okay. And I hope that things make better sense because you can see the cursor. Is it? Is it better? Okay, keep
Yeah,
on
it's
nodding.
helpful.
Yeah, good, good. Hopefully you can follow what I'm trying to say that way. Okay, so is this state really minimum uncertainty? So let's just go ahead and compute that. So I already mentioned that X expectation value is given by the real part of F. And X squared expectation value can also be computed readily. So X is A plus A dagger over square root 2. So X squared is A plus A dagger squared over square root 2 squared. So that's 1 over 2. And I just expand this out. So when A is on this side, acting twice because of the square, that will pull out eigenvalue F twice. So that's F squared. If you have A dagger squared out of this whole thing, then A dagger can be now viewed to be acting on F bar, and that will pull out eigenvalue F star, as I mentioned on the previous slide, and then twice. So I get F star squared. Now comes the cross term. And cross term has A dagger A in it, and A dagger A can be viewed as A acting on F ket, A dagger acting on F bar. So A acting on F ket pulls out F. A dagger acting on F bar pulls out F star. So that way I get 1 power of F star F. But I also have the other ordering in the squared, A dagger instead of A dagger A. But A dagger can be commuted by using commutation relation that A times A dagger is A dagger A plus 1 using commutation relation. So we already computed what A dagger A is, sandwiched between these coherent states. That's just yet another factor of F star F. So this now becomes twice. But I do have to add this 1 when I commuted the order of F and A dagger. So this is the end result. So X squared expectation value is given by this combination, and this one piece comes from changing the ordering between A and A dagger operators in the cross term. Okay, I hope that's clear. And again, I stop in a couple of minutes and you can ask questions if anything's not clear. So that allows us to compute the uncertainty in X. I have X squared expectation value, that's this one. I subtract square of the X expectation value, that's this one. And if I take square of X expectation value, that's 1/2 times F plus F star squared. That's exactly what these three terms, first three terms are. So they all cancel out. But this last term 1 remains. So that ends up this answer 1/2. So this is how I can compute the uncertainty in X. And as you can see, it doesn't grow even if you go to a state with larger N or larger energies, it stays 1/2, no matter what the eigenvalue F is. And we do the same thing for momentum. So P is F minus F star, and this is the expectation value of the P operator. And if you compute P squared expectation value, I go through the same set of steps. Then I get this one. Again, there is this 1 coming out from this commuting the ordering between A and A dagger operator from the cross term sandwiched between the coherent states. And compute the uncertainty. So I take this result, which is the expectation value of P squared. I square the expectation value of P and subtract it. Once again, square of the expectation value cancels the first 3 terms in the expectation value, the square of the operator. The only thing that remains is 1 coming out of the commutator, A and A dagger. So end result is 1/2. So uncertainty in X is 1/2. Uncertainty squared in X is 1/2. Uncertainty squared in P is 1/2. So if you multiply them together, delta X is 1 over square root 2. That's square root of this. Delta P is 1 over square root 2. So if you multiply them together, you get 1/2. And if you remember, we've been using this unit to just simplify expressions where H bar is 1 you can recover h bar now based on dimensional grounds. So this has to be proportional to h bar. So delta x delta p is indeed h bar over 2. That's the smallest Heisenberg would allow us. So this is the minimum uncertain state indeed. So the kind of picture I drew over here, where you have this minimum size area sitting on this circle, is indeed realized by the coherent state we defined on the previous slide. So our guess turned out to be correct. All right, so let me stop here once again to see if there are any questions. And it would be great if you actually show yourself when you ask question. No questions? I hope you can do this, right? All right, so, of course, there will be more opportunities to ask questions later. So let me just keep going for now. So we did find that indeed the coherent state is a minimum uncertainty state. Given that, it really starts to look like this mimics the classical motion, but so far we haven't really discussed motion, namely time evolution of the coherent state. So let's see how this coherent state evolves with time. So that's the next discussion here. So this is the definition of the coherent state. Again, I have the same typo over here because I just copied the previous slide. So you should drop this sum. Sorry about that. But anyway, this is the definition. So what we do is to see how this state evolves in time. And as you have seen in the quantum mechanics class, I believe, the time evolution is given by this unitary operator, where you have Hamiltonian in the exponent, together with time and minus I over h bar. So one way to see this is that if you take time derivative of this state, together with this unitary operator, then time derivative will pull out h from the exponent, very similar to what we have just done with the coherent state, right? So time derivative will pull out h. So time derivative is given by h acting on the state. That's nothing but the Schrödinger equation. So this is actually a formal solution to the Schrödinger equation that any state would evolve according to the exponential of the Hamiltonian as the unitary operator. So that's true for any state in the quantum mechanics. But the reason why using this unitary operator is a good thing for us is that I don't need to solve the differential equation anymore. I know exactly how time enters this. And also, when Hamiltonian acts on this expression, given in terms of the number states, we know the eigenvalues too. So when I act this unitary operator on this coherent state, these things here are just numbers. So I can commute this operator with this number coefficient here. Then this unitary operator is acting directly on the number state n, together with this normalization factor. And h acting on number state n just pulls out its eigenvalue, h bar omega n plus 1/2, as you all know. So all this the unitary operator does is pull out this phase given by its energy eigenvalue. Now you have this exponential phase factor, which is now a number. There's no operator left anymore. So I can deal with this very easily because they are all commuting numbers. And one thing you'll find is that there's an n in here. And n in the exponent means the whole thing is raised to nth power. So I can combine this e to the minus I omega t after canceling this power of h bar in the numerator and denominator. So this n piece here will correspond to e to the minus I omega t raised to nth power. So I can combine this together with f to the n in the definition of the coherent state. So this thing is f times the e to the minus omega t raised to the nth power. But I haven't taken care of everything yet because there's additional 1/2 here. And so this 1/2 certainly is not part of this nth power. So I have to separate that out. So I leave it alone at the end of this expression. But the reason why it is good to write it this way is that if you compare this part of the expression without this last factor of e to the minus I omega t over 2, this expression is the same expression as the coherent state, definition of the coherent state up here, except that this complex number f is now replaced by complex number f times additional phase factor, which is time dependent. So what that means is that time evolution would make coherent state into yet another coherent state where the eigenvalue f is now changed to f times e to the minus I omega t. And that's exactly what we wanted. So when you look at this phase factor e to the minus I omega t, that's a phase factor, a complex number with norm 1. So all it does, e to the minus omega t, is to keep changing the phase along this circle. So as time evolves, this eigenvalue f, represented by a tiny circle here, would change its position along this circle, which is nothing but the change of the phase. So if you remember that f really corresponds to the expectation value of x and p, and when f changes by this phase factor e to the minus omega t, what that means is that x and p changes by cosine omega t and sine omega t. That's exactly what we know about the motion of the pendulum. The only thing that is left out is this still overall phase factor of e to the minus I omega t over 2, but that's just an overall phase of the state. Whenever you compute probability, overall phase doesn't matter. So in the end, the essential part of the time evolution is really changes eigenvalue f as a complex number to move along this circle so that x and p changes by cosine omega t and sine omega t. So now you start to see that coherent state really does mimic the classical motion of the pendulum. So there was a lot on this slide. So I guess this is, again, good time to stop and see if there are any questions. No? Everything okay? Okay, so let's actually try to see this more explicitly, what time evolution does. So what I show here is that I take the position space, ket, namely the wave function of the coherent state as a function of time, and take the absolute square of that. So that gives you probability density of the position x at any given moment. So let me first show you in the case when f is 2, which is what a small number, and I take this following unit, and I apologize that now omega is chosen to be 2 pi instead of 1, just because omega has to do with the frequency, and my animation turns out to be too slow if I choose omega to be 1. So this is just an arbitrary choice I made so that I can show this animation. So let me do this. So this, the yellow line shows this x squared potential of the harmonic oscillator. And I'm imagining that this wave function is sort of sitting on that potential, showing this probability density as a function of the position x. And so at time 0, this is the probability density of the wave function, which looks exactly the same actually as the ground state wave function, but pulled away from the ground state minimum potential by a finite spatial interval. So that, again, is part of the homework problem. Coherent state, when f is real, is the same thing as the ground state wave function shifted in the space direction. So that's exactly what this state is. Then I let the time evolve and see what happens, and this is what it does. And the fact that it stops a little bit is just because of the artifact of the animation produced by Mathematica. So that, don't worry about this. It's not meant to stop. So just keep swinging back and forth. And that's exactly what you expect for the classical pendulum, right? But because of the probability density here is fairly spread out, even though the motion itself mimics a classical motion, it still doesn't quite look like a classical particle where the position is supposed to be a dot instead of the something that has a spread in it. So when F is 2, the quantum uncertainty is still very much sizable. So that's what you see here. So coherent state does mimic the classical motion of a particle, but when F is small, it still looks like very much a quantum state, very fuzzy, very much the large uncertainty involved. But now I said that F is small here. I go to larger F. Let's say F is 10 now. Then I do the same thing. And you can see now that the wave function looks a little bit more tighter, because how much the wave function swings in position space is basically given by F. And for this particular unit I chose here, it's actually F over square root pi. So when F is 10, F over square root pi is something like 6. And indeed, the X swings back and forth between 6 and minus 6. But uncertainty is always 1/2. That's what we learned before. So compared to 6, 1/2 looks kind of small compared to previous situation where 1/2 looks quite sizable compared to 2 over square root pi, that's like 1.2. So once F is larger, then the spread of the in position space starts to look smaller and smaller. So that's why wave function looks tighter in position space than the case when F is 2. So if I go all the way to F equal 100, then it starts to look pretty much like a classical particle. So you don't even see the size of the wave function really now. And let me see if I can stop this for a second so that you can observe where the wave function is. So this little blip is the probability density of the particle. And now you see it's almost a point. It is still spread out because, you know, Heisenberg tells us that there's a minimum uncertainty anyway. So it is so spread out in such a way that the uncertainty in X is still given by 1/2. But compared to the size of X itself, which is given by something like 60 now, sorry. So compared to the overall size of X, which is something like 60, oops, oh, I keep making a mistake. Okay, good. So overall size of the uncertainty is like 60. And compared to that, overall size of X is like 60 here on this plot, but the size of uncertainty is like 1/2. So the uncertainty starts to become pretty much negligible. So what you see here is that when you have a coherent state, but when the eigenvalue annihilation operator is large, then that's a situation that will mimic the classical motion of the pendulum the most. And I said this last time too, so we actually end up using this coherent state when we quantize the electromagnetic field, when you can talk about photons. We need to find a way of describing classical electromagnetic wave using photons. So how come that once you have photons as individual particles, collection of the photons can behave as if it were a classical electromagnetic wave? And if you don't get a classical electromagnetic wave, your Wi-Fi in your home probably doesn't work. It's a microwave. That's a classical electromagnetic wave. If you think of them as individual photons, then how do you transmit the signal of this video transmitted over the Wi-Fi to your computer? So you have to really treat that as a classical wave, as a microwave, as a solution of the Maxwell's equation when you can talk about these electromagnetic waves. So the fact that you can have a collection of photons, individual particles, which can behave like a classical wave at the end of the day, relies on this coherent state for its description. And we'll come back and talk about this. Don't worry about that for now. But I'm just giving you the reason why we are talking about this coherent state using harmonic oscillator for the moment. And this is a demonstration that coherent state with large eigenvalue really does mimic a classical pendulum which ends up becoming a classical electromagnetic wave when we get to talk about it. Okay, so let me pause here once again to see if there are any questions.
Yes, I have a naive question. Did you cut off the infinite sum of the coherent state? Because the wave function is supposed to be Gaussian, right? But the tail of the wave function you show here, it seems like doesn't just die off like, can you see my hand? Like flatly, it goes somehow up a little bit.
It does, it does. So the way I actually made this animation is that I wanted to show that the particle is really moving on this quadratic potential of the harmonic oscillator. So I added this wave function squared on top of this potential. So when the wave function dies off to approach this potential energy, and that means it's actually going to zero. So I realized that can cause confusion, but to mimic the motion of the classical particle sitting on a classical potential well, I thought this was the best way to actually demonstrate that. So the wave function is still Gaussian. It does die off to zero, but in this animation, dying off to zero corresponds to approaching this curve for the potential energy, which is quadratic in X.
Okay, cool. I see. Thank you.
Thank you for asking question so that I could actually clarify this trick I used to make this animation. Thank you. Any other questions here?
Yeah, Professor, I was just wondering
Go ahead.
A similar animation would look like for the regular quantum harmonic oscillator.
I can't hear you very well. Can you speak up more?
Yeah, I was wondering what a similar animation would look like for the typical quantum harmonic oscillator that is not a coherent state.
Okay. So the typical number state of a harmonic oscillator is a stationary state, and time evolution is just the phase given by its energy eigenvalue. We actually used that in the algebra on the previous slide. So when you compute the squared, absolute square of the wave function, which depends on time only by a phase factor, absolute squared, then phase factor drops out. So the wave function squared doesn't depend on time. And that's exactly what's meant by the name stationary state. Energy eigenstate is a stationary state, namely that probability density doesn't change as time goes on, hence stationary. And the shape of the wave function is something you might remember from this L-Mead polynomial at times Gaussian. And it basically has something like this. You know, there's a function that oscillates back and forth n times. The ground state doesn't oscillate. The first excited state oscillates twice and 3 times and so on and so forth. So it kind of a zigzag function, but it stays put. And it's always spread out over the entire range of X. So that's why uncertainty in X was so large if you go to large n eigenstate, because it's really spread out over the range given by this energy of the particle. Am I answering your question?
Yeah, thank you.
Okay, good. Any further questions on this? You know, harmonic oscillator is something you might have thought that we know real cool, but there's still something interesting about it. And we are going to use that something interesting for the rest of the discussion for quantizing field. So anyway, so that's what I wanted to discuss about the coherent state. No, if there are no further questions, I'm going to move on, or there's a chat. That's neat, really epic. Thank you. I spent quite a bit of time making this animation, so I appreciate that comment. Okay, good. So this is the coherent state, and now we know what it does. It really mimics the classical motion of a particle in the large F limit, and we're going to use this to describe the classical wave at the end of the day in quantum field theory. There's just one last thing I'd like to mention about this. So when you're talking about uncertainty in X and uncertainty in P, there's another way to think about uncertainty if you're staring at this little circle over here. You can ask the question, what is the uncertainty in the radial direction? And as you remember, the n number operator is half x plus p squared. So this radial direction corresponds to n. So I can view this size of the circle as an uncertainty in n. But if I take one of the variable to be this radial direction, another direction should be this angular direction or phase, then I can speak of the uncertainty in this angular direction too. So that's when we talk about number phase uncertainty, namely that uncertainty in the radial direction is a number uncertainty, uncertainty in the angular direction is the phase uncertainty. And it seems to be that there is the minimum size of the area, so one can define this kind of uncertainty in the number as well as the phase. And so we would like to discuss that, but one problem is the following. We know what number is. We know what the number operator is. It's given by A dagger A. But what the phase is something we never talked about. So the way you can define the phase, again, remembering that this is meant to be the eigenvalue of an annihilation operator, is something like this. So n is A dagger A. We knew that all along. But then you can try to write an annihilation operator as the square root of n times this phase. And then Hermitian conjugate of this, when you take Hermitian conjugates, ordering become the opposite, right? So n square root goes to the left, and e to the I theta goes to the right. But Hermitian conjugate turns I into minus I, so this will be the expression for A dagger, if you write A this way. And I chose this expression in such a way that when you compute A dagger A, this phase factor cancels. I hope you can see that. So the phase factor cancels between A dagger A, then that turns into square root n times square root n, which is nothing but n. So this is how I can recover this definition of the number operator given by A dagger A. So that way, I now have managed to introduce the phase as a part of the definition of the annihilation operator. But again, this is actually not quite rigorous. We are physicists, mathematicians, not mathematicians. Reason being that when n is 0, then theta is ill-defined because A, the whole thing is 0. The number 0 doesn't have a phase. So there is some ill-defined nature in the definition of the theta given by this expression, but we have to live with it. So as long as we are always interested in a case when the f is large enough, then we probably don't need to worry about that too much. So again, this is the attitude of physicists. If something is working more or less okay, we might accept that. So theta is ill-defined. We accept it and see how far we can go with it. So remembering this commutation relation between n and a, number operator and annihilation operator, given by this expression. Inside this a, I have this square root n, but square root n commutes with n, so I can take that out. So all this is telling you is that now we learn that n acts as if derivative with respect to theta, so that I recover the standard commutational relation between n and a. Again, this is a heuristic, and theta is ill-defined when n equals 0. We have to keep that in our mind. But modulo that caveat, I can treat n as if it's a derivative with respect to theta, which means n theta commutation relation would be I, which then means that there is an uncertainty principle that delta n times delta theta has to be bigger than 1/2. So this is what we call the number phase uncertainty. And this is actually of practical value when you talk about laser, and especially when you're doing quantum optics experiments. You would talk about quantum fluctuation in laser. So laser contains a huge number of photons, but it's actually not exactly fixed, the number of photons in it. There is an uncertainty associated with it. And if there is no uncertainty n, if n is totally fixed, theta becomes totally uncertain, then the laser becomes not coherent electromagnetic wave. You need to have theta well-defined at some level so that you can talk about coherence and interference and so on and so forth. So in order to have coherence of the laser, you need to make number a little bit uncertain, it turns out, because of this uncertainty relation. And again, we'll come back and talk about this. You don't need to understand this now because we haven't quantized the photon yet, but it's coming. So in order to have a coherent phenomena where theta is somewhat fixed so that you can talk about the interference pattern and so on and so forth, you need to make n uncertainty correspondingly to satisfy this uncertainty principle by Heisenberg. So that is what is called the number phase uncertainty. Okay, let me pause here again if there are any questions.
I'm sorry, can you explain why n equals the derivative again? Because
Yeah, so what I derived here is that modulo this caveat that theta does get ill-defined when n equals 0, we need to satisfy this commutation relation between n and a. And we decided to write a as this e to the I theta times square root n, so that this expression recovers n being a dagger a. So that's the expression I'm going to use. So then NA commutator has to be minus A. So with this expression of A, it needs to satisfy this commutation relation.
Mm-hmm.
But
yes,
n square root, of course, commutes with n. So I can take this out from the commutator. Then what I have to make sure is that n e to the I theta commutator becomes negative e to the I theta. I'm factoring square root n from both sides of the equation. So if n e to the I theta commutator is supposed to become negative e to the I theta, then I can take n to be I del del theta.
okay.
So that's the heuristic argument.
Okay.
And then once you accept that n is I del del theta, then I can derive this expression.
Yeah, the rest
from this,
just
yeah,
straightforward.
The rest follows. Yes. Yeah. Okay, thank you.
Okay.
Any further questions here? Okay, so now I showed you that the number and phase uncertainty principle exists. And then the next question you would wonder is that, okay, we know there's a such thing called n eigenstate. Is there such a thing of phase eigenstate? And there is, modulo this caveat I mentioned about n equals 0. So let's actually look at that. But anyway, so just showing graphically, this n and theta uncertainty is, as I said already in words, n uncertainty is the spread in the radial direction, and theta uncertainty is the spread in this angular direction. And because we know xp uncertainty principle tells you that area has to be bigger than h over 2, no wonder that n uncertainty and theta uncertainty, their product would be bigger than h over 2. So it's sort of at least intuitive, makes sense, I hope. So I can build phase eigenstate. So how does it look like? Well, I have to say this is almost an eigenstate. And you can sort of guess it. Using this n theta uncertainty principle, if you want to have theta completely well-defined, so that's an eigenvalue, then n has to be completely uncertain, right? The delta n has to be infinite if delta theta is 0. And you know this from other examples in quantum mechanics. When you're talking about position eigenstate, when x is fixed, then p is completely uncertain. When you have the momentum eigenstate, p is fixed, then it's a plane wave, then probability density is constant throughout space, so x is completely uncertain. So in the same way, if you have the phase eigenstate, delta theta is 0, then n is completely uncertain. So that gives you a good guess on what the phase eigenstate should look like, namely that you sum over all n's with specified phase factor. So I sum over all n eigenstates given by the weight, given or by e to the n I phi. Phi is a real number. This actually turns out to be basically the phase eigenstate. So let's see that. I'm going to act annihilation operator on this phase state, but I would like to get rid of the square root n. So what I'm going to act is e to the I theta operator written as a times 1 over square root n. That's where I get a little scary, because when you take 1 over square root n, acting on number state 0, that returns infinity, 1 over square root 0. That's why I define this state to be sum from n equal 1 to infinity to avoid that problem. So let's go ahead and do that. So acting e to the I theta on this state, I rewrite e to the I theta as a, an addition operator, times 1 over square root n, so that this 1 over square root n cancels the square root n, so that I'm left only with e to the I theta operator. So that's what I have here. And because of the careful choice I made to sum only from n equal 1, this 1 over square root n is not singular, at least. And that n becomes the number n that goes from 1 to infinity. So 1 over square root n as a number now, together with its phase factor. And then I have this annihilation operator A acting on the whole thing. And these things are numbers. I can commute A with these numbers. So A now acts directly on the n state. And we know what it does. A lowers n state to n minus 1. So n minus 1 here, together with this normalization factor square root n, right? And this square root n cancels this 1 over square root n over here. So I get something simpler. Then you remember n is a dummy variable. I could have labeled L or M or K plus 2 or whatever you like. So I changed my label n to n minus 1 instead. So I'm going to call this n minus 1 my new n. Then n in the exponent turns into n plus 1 instead with a new n, right? And I have to be a little bit careful when I relabel a dummy variable, because the range of the sum now changes from 1 to infinity to 0 to infinity, because the ground state, 0 here, will correspond to n equal 1 with the old n, which is part of this sum. So with the new n, ground state should also be included in the sum, so now the sum goes from 0 to infinity. But the main point here is that after relabeling n, the only difference from the state I defined over here is that the phase is n plus 1 instead of n. So I factor 1 out, and that's e to the I phi in front. The rest is this. And this is more or less this state I defined over here, except that now the sum goes from 0 to infinity. So I do have to add the ground state in addition to this state phi. And this is where my definition of the phase operator fails. But you can see that more or less, this state phi has the eigenvalue e to the I phi if I ignore this ground state portion that comes in the last expression. So this is the way you can define quote unquote phase eigenstate, parenthesis open, almost, parenthesis close. So that's the phase eigenstate. And from this definition of the phase eigenstate, you can see that n is summed over all ranges from 1 to infinity. So n is completely uncertain. But instead, I have phi, the phase, basically fixed as an eigenvalue, with this caveat about this ground state portion in it. So this is almost eigenstate of the phase operator, where you can see this number phase uncertainty principle in display. To make phase certain, you need to make the number completely uncertain. And the coherent state is the good compromise between the two, where phase and number are both more or less well-defined with a minimum uncertainty. If you define n eigenstate, that's the state that gets spread out throughout this circle as a band, as we talked about, then phase is totally uncertain because it takes every direction with an equal probability, right? It's a band all the way around. So phase is totally uncertain by 2 pi. So that's the case where delta n is 0, delta theta is the maximum. And the state we just talked about has n completely uncertain because you sum over all n's along this radial direction, But at the same time, you can squeeze the uncertainty in the phase direction so that you have this eigenvalue e to the I phi almost. So the number phase uncertainty does make sense. You can build n eigenstate where theta is totally uncertain. You can have a compromise state, like coherent state, where both n and theta are well defined enough if the whole thing is large enough. Or you can define a state where n is completely uncertain so that the state is eigenstate of the phase almost. So that's a demonstration about the phase number uncertainty. Okay, any questions on this? Is it okay? All right, so now we move into quantum field theory. Let the creation begin. So we're gonna use creation operator we introduced in the harmonic oscillator, now literally as an operator that creates particles. So how do we do that is the discussion I'm gonna start now. Okay, so now we make this huge jump. We have this commutator between annihilation and creation operator. We got very familiar with the harmonic oscillator. And remember, I'm putting this label n and m so that I have multiple harmonic oscillators. And I didn't write it here, but a n of different n commute with each other. A dagger m of different m commute with each other. The only non-zero commutator is a and a dagger when they refer to the same harmonic oscillator. But we can have infinite number of harmonic oscillators. And so that's the situation we have in mind. And now we make this big jump going from quantum mechanics to quantum field theory. We're going to use this A and A dagger operator literally as an operator to annihilate a particle and create a particle. So creation operator A dagger is an operator that creates a particle, and A operator is annihilate a particle. And then we can think about what this label N stands for. And to make discussion simple, and this is I never actually did this way of introducing quantum field theory. This is my first time in trying it on you, so you tell me if that makes sense. So to make the quantum field theory as intuitive as possible, I'm going to treat this N label to be the possession for now. Namely that AN dagger is an operator that creates a particle all of a sudden at the particular position N. And similarly, we use the annihilation operator AN as an operator that removes a particle from position N. So that's the way we now view what this creation and annihilation operators actually do. So this is a huge jump from quantum mechanics to quantum field theory, and you will see also later why this is actually a field theory once we actually take the limit of a continuum. But let me just get started with a case when the particle is supposed to be on this one-dimensional lattice. And you can view this as an exercise in condensed matter physics, where electron has to occupy a particular lattice site in condensed matter system. So we view now an operator A dagger to be an operator that can create a particle here. So at the beginning, there's no particle. All the sites are empty. But now I can talk about a state where this site is now occupied by a particle. Or maybe 2 of the sites are occupied, 3 of the sites are occupied, or 4 of the sites are occupied. And the way we use the creation annihilation operators is that, okay, the state with no particles at all is 0, which is we call the vacuum state, which is annihilated by the annihilation operator of all n, because at every n, which refers to these sites, though there are no particles, so when you act an on it, there's nothing to remove, so you can't lower the state anymore, hence 0. So that's a definition of the state we call vacuum, no particles. And that's the meaning of the word vacuum. And now you can see how you're going to use the creation operator on top of this. So when you put particle here at site 6, 1, 2, 3, 4, 5, 6, then you act this creation operator on the vacuum state. That is the state with one particle in the system. Then now you see the rest. I can have two sites occupied by acting creation operators twice on site 6 and site 14. And I can create yet more particle on site 2 by acting creation operator 3 times on the vacuum state. And each creation operator specifically creates a particle at site given by this label. So A2 dagger creates a particle at site 2, A6 dagger creates a particle at site 6, A14 dagger creates a particle at site 14. And finally, this 4-particle state will be given by this. So you create particles at site 2, 6, 11, 14 by acting creation operator for those specific sites on the vacuum state. And that's how you use creation and annihilation operators. So we use creation operator literally to create a particle at a particular position. And when you would like to remove a particle, you act annihilation operator on that position. And they satisfy the standard commutation relation of A and A dagger, giving you 1. So this is what the quantum field theory is about. And as I advertised last week, now we have a Hilbert space, which includes states of different numbers of the particles. That is something you could never done in quantum mechanics. In quantum mechanics, you have to specify the number of particles first. And that's when you know the dimension of the Hilbert space, how many x's you have to specify for a given position eigenstate. Then you can write the Schrödinger equation, you can try to solve it, you can go for energy eigenstates and so on and so forth. But throughout that process, n stays fixed. But here, the same Hilbert space, we built out of this vacuum state by successively acting creation operators on it. This Hilbert space contains states with different number of particles. So using this Hilbert space, we can talk about physical processes where the number of particles can jump from 3 to 4, or 1 million to 1 million minus 1. So this is now a big Hilbert space, which contains all states with different number of particles in it. And you can freely go up and down in number of particles in this big Hilbert space. And this Hilbert space is called Fock space, F-O-C-K. Fock is the name of the person who invented this kind of Hilbert space. So we now have this huge Hilbert space, Fock space, built out of the vacuum state and acting creation operators on it, so that each creation operator creates particle at a specific position. So that's the idea of the quantum field theory. So let me pause here for the moment to see if there are any questions about this. This is a conceptual huge jump we made from quantum mechanics to quantum field theory. Questions?
Yes. So
go ahead.
Do you need to discretize space-time for this to work, or is there...
No, we will come back to continuum space-time later. So this is just a simple way of introducing the idea of creating a particle at a given position. And now I put them on a lattice with a finite interval d between the lattice sites. But in the end, I will take the limit where d goes to 0. So the discretized space now becomes a continuous space at the end of the day. So this is just part of the argument I'm using, hopefully would make it look a little bit more intuitive rather than introducing the continuous space-time from the very beginning. So this is meant to be an introduction to a quantum field theory defined on continuum space. But I hope, at least at this stage, it intuitively makes sense. So that's the reason I'm doing it this way. Does that answer your question?
Okay. Yes, and I also wanted to ask, are the states in the Fock space just the existence of different numbers of particles, or does it also say something about the physical state each particle is in?
So that's an excellent question. I wanted to come back and mention this. So when I have this 4-particle state, for instance, I remember I told you that a dagger of different positions commute with each other, and annihilation operators at different sites commute with each other. So what that means is that if I change the order between A11 dagger and A14 dagger, nothing changes. It's the same, which means the particles I put at site 11 and site 14, I can interchange them without changing the state. What that means is that interchanging particles leaves the state unchanged, namely that the state I constructed here in the Fock space is symmetric under the interchange. And I believe that will come up here. And this is the Lagrangian, of course, we always use from the harmonic oscillator. And this is symmetric under the interchange of any of these particles. So if we have 4 particles here, I have 4 factorial way of writing this product, but they are all the same. Namely that my state in this Fock space is invariant or symmetric under interchange of any of the 2 particles in the state. So this Fock state is automatically incorporates quantum statistics of bosons. And again, somebody asked the question before, what happens when we with the fermions? We'll come back and talk about that later. So for now, this is the Fock space we built out of this canonical commutation relations of annihilation creation operators. And Fock space does contain states with different number of particles. That's really a huge progress so that you can describe processes where number of particles can change. But by doing so, the quantum statistics is automatically built in. You don't need to write the multi-particle wave function and impose symmetrization by hand like what you used to do in quantum mechanics class. The state is automatically symmetric under interchange among the particles. And so in this particular case, that's a boson. It obeys both Einstein statistics. So thank you for asking that question. Any further questions at this stage?
How do you know like the distances between like noticing the the particles that are not actually created yet in between the blue? How is it like knowing the actual distances between particles that are created, for example, to know like, okay, I need to put it at this specific spot, or is that already like engraved into the definition in the first place?
Yeah,
like
so it's basically built into the definition of this vacuum state. So vacuum state is defined as a state that gets annihilated by annihilation operators for all sites on this lattice. So that's a requirement that this vacuum state has no particle anywhere. That's the meaning of this statement, which has to be satisfied for all n. And because okay, go ahead.
So the vacuum state basically knows exactly like the specific spots that you need to be, do you need to be able to put a new particle in the first place?
Well, so that where you put a new particle is specified by this label 6 in here. So when I use this operator, creation operator A6 dagger, this operator specifically creates a particle at position 6. A14 dagger is an operator that specifically creates a particle at position 14. So the vacuum state doesn't distinguish one site from another because there's no particle anywhere. But when you create a particle, you need to specify where you pop the particle in. And that's when you have to use particular creation operator that refers to that particular site.
Okay.
Does that answer your question?
Yeah, that makes sense. The vacuum
state
is the one that
good.
makes understand.
Any further questions here? Okay, now, and looking back at this Lagrangian, so this is what the Lagrangian we use for the harmonic oscillator. So we are copying the same Lagrangian for every single site. So the entire Lagrangian will be just the grand sum of it. So IH bar A dagger A dot minus H bar omega A dagger A is the Lagrangian we derived for a single harmonic oscillator. Now I'm writing the Lagrangian, which is the sum over all of them. And in particular, this second term in the Lagrangian is meant to be the Hamiltonian. So it's a PQ dot minus H. That's the way we wrote the Lagrangian. So this piece is the Hamiltonian, again, summed over all n, right? So that's the Hamiltonian we got. So now comes, I think, the pole. So here's the question. So I decided to put a particle at specific sites. And this is the Hamiltonian that dictates how states would evolve in time, right? So Schrödinger equation tells you the Hamiltonian is the operator that moves the time forward. We talked about unitary evolution operator like 20 minutes ago, the exponential of the Hamiltonian operator. So once you know the Hamiltonian, you know how these states evolve in time. So here, I created particles at specific spots. So it looks something like a position eigenstates here. So now comes the question. Launch pole. So with this Hamiltonian, how do these states evolve with time? So the first choice is that once you put a particle on a specific site, it just stays there put. It doesn't go anywhere. That's the first choice. Second one is that, well, I remember what happens to a wave packet in quantum mechanics. Wave packets is that if you have a Gaussian wave packet, that starts to slowly spread out. So maybe the particle doesn't stay put on a particular site, it starts to spread out. Or maybe the third choice is that I know what happens to the position eigenstate in quantum mechanics. Once your particle at a specific site position eigenstate, the time evolution would instantly make it totally blurred in space. So these are the three choices. It stays put on lattice site, it starts to slowly spread out, or instantly gets totally spread out. So these are the three choices. Okay, you guys are now casting ballots. Interesting. It looks like it's evenly split. Good. All right, some of you are still thinking. Okay, 20 of 24 voted, so maybe I stop here. So, in poll, show results. So, rather a few of you chose the option 3, but pretty much sort of equally split between the choice 1 and 2. So, about half of you think that it stays put on the same lattice site. The other half think that it starts to slowly spread out. And the 3 of you think that it instantly gets totally blurred for the entire space. Okay, so what is the right answer here? Well, we have the Hamiltonian here, right? And that's the sum over this harmonic oscillator Hamiltonian for all sites. So when you act this Hamiltonian on these states, on a first state, I have one A dagger here. So 1 out of this A dagger A picks up the eigenvalue 1. So this state has eigenvalue h bar omega as the energy eigenvalue. Second one, I use this Hamiltonian for the site 6 once, and that returns eigenvalue 1. And also for the site 14, and that returns eigenvalue 1 because of this A dagger. All the other A dagger A vanish because you haven't created a particle there yet, so the eigenvalue is 0. So I sum eigenvalue h bar omega 1 for 2 of the sites. So eigenvalue is 2h bar omega. So this is 3h bar omega, this is 4h bar omega. But the point here being that they are energy eigenstates, which means they are stationary states. So the state doesn't change. So eigenvalues of Hamiltonian are stationary states. When you compute the expectation value squared, nothing changes because the overall phase factor drops out from the wave function squared. So the answer to this question was that all of these particles stay put forever. They don't move. So that's the answer to this question. But now we have to think a little bit more about how we can let them move. So we managed to create this Fock space where particles can be put at particular positions. But in some sense, this is an infinitely heavy particle. They never move. And that doesn't give you interesting physics yet. So we need to describe a situation where the particle you put on lattice site, say 7, can move to 8 or 6. So how can we make that happen? So I'm running out of time now. So I give you just upshot on where we're getting to and then stop there. So suppose you put a particle on the lattice site 6. We need to find a way of letting it move to lattice site 7. So the way you can make that happen is to change the Hamiltonian to add the following term, which mixes up creation and annihilation operators between site 6 and site 7. So if I use this operator, acting on this state where particles are site 6, you have particles site 6 here, which you can now annihilate with the annihilation operator. So this particle is now gone. So this is now empty at site 6. But instead, you create a particle at site 7. So now the particle is created at site 7 now. So it doesn't look like it's moving quite, but you annihilate particle at site 6. You instead create a particle at site 7. So this disappears and pops up over here. And that's the way you can represent the particle moving from site 6 to site 7. So what we're going to do on Friday is to use this kind of term in a Hamiltonian to find out what kind of energy eigenstates you get by modifying the Hamiltonian to include this possibility that particles can now move on this lattice. So that's how we can begin writing down the quantum field theory. You can create annihilate particles everywhere you want. We can also let them move. And then in the end, I take this continuum limit of taking the limit of lattice spacing go to 0. And that's how I discover quantum field theory for you. So that's the plan. Okay, I stop here. And any questions, welcome. No?
Cool.
Somebody wants to speak? Yes, go ahead.
Yeah. Oh, what is it? It's kind of like I guess it's not super important, but it's like I noticed just it's like a general thing, just quantum mechanics. Like what is it? Like I notice every time like when we have a commutator of two operators that resolves to something that's proportional to like identity, that like the operators like one of the at least one of the operators always seem to be like an unbounded operator. Like I noticed that because like when you did a dagger, and when you did the commutator of a dagger, it resolved to 1, and then you put the little heuristic argument that like a was equal to partial a dagger. Yeah, like what is it? And like I know like the derivative is like an unbounded operator. Like, is there any significance to that?
Well, so we have seen an example where the commutator is not just a number, right? So if you look at an A commutator, for instance, that's A, not a number.
Yeah.
So there's no guarantee that commutator always turns out to be a number. So this is a counterexample to this.
Yeah. Well, but what is it? It is like I don't know. Like, is it always the case? Like, for example, like you see right there, it's like the commutator of n and like theta is equal to I, and that's like proportional to identity. And like you put that n was the was like a derivative. Will that always be the case if you have two operators that like if you put two operators on a commutator and it resolves to something proportional to identity, that one of the operators has to be unbounded?
Yeah, so the issue is that when you have a commutator of two operators, which gives you something proportional to identity, that's the situation where two operators are canonically conjugate to each other, like x and p, and a and a dagger. And n and theta are also canonically conjugate variables. So the quantum mechanics is built up on this commutation relations, and not every commutators are given by identity matrix, identity element. But when two operators have the commutator proportional to identity element, that's the sign that these two operators are special relationship to each other, namely that they are canonically conjugate to each other. So that's a situation we know how uncertainty principle works. And that's why we want to define number and phase operators so that we can use the standard definition of uncertainty principles. But that applies only to the situation where commutator is proportional to 1. Therefore, two variables are canonically conjugate to each other.
Okay. All right. Okay. Thank you.
Okay. Good. Thank you for asking your question. Any further questions on this? So anyway, we made a huge jump today, and it takes a little bit of time to get used to this, but we will go through this over and over again. Hopefully over time that will sink in. So if you are totally baffled today, you are not alone. The first time I saw this, I was so totally baffled too, but we'll get we'll get used to it. So don't worry, we'll get used to it. And you'll see the same process once again on Friday, and then we go from there. Okay, so as usual, I post the slides after fixing the typo on B courses and a video on YouTube. And so if you have any thing you want to look up again, then you can look at the slides and the videos. All right, so see you on Friday.